Welcome to Virtual Process Control Laboratory. I am Professor Uttam. Today I will discuss about flow measurement using a rotameter and a orifice plate. So we will go to this open loop system, which is a physical system which measurements are done manually, and we calibrate a orifice plate flow meter and a rotameter here. So you will find here the inbuilt stopwatch which can be started and stopped as and when required, and there is a pump which draws water, and it shows it is going through a pipeline of ID 22 centimeter through an orifice plate of 5.5 centimeter hole, and it then finally goes to a rotameter and falls in a vertical tank which has a capacity to hold 160 liter of water, and excess water will overflow back to the reservoir. And there is a inlet valve here which can be opened clockwise direction and closed in the anti-clockwise direction. Similar valve is at the drain as and when required. When we start the experiment, we start from zero level just by keeping closed this valve and draining all this water, and its inbuilt stopwatch which can be started and stopped with these two buttons, and the corresponding display of the run number, time, liters accumulated in this tank, and the calculated flow rate in liters per minute and millimeter of mercury pressure drop across this manometer, and average velocity will be calculated, will be shown here, will be displayed, and finally all the experiments up to 12 runs can be taken by this valve opening and closing, and calibration chart can be clicked to get the final calibration graph and as well as chart. Now we take the first run for few seconds and start the stopwatch. You will see that run number, time in second, liters accumulating, and the flow rate calculated, and millimeter of mercury pressure drop across this manometer, and the average velocity to the orifice plate. All are displayed here simultaneously. And since up to 1/6 liter filling, it will take a lot of time to reduce the time of video. I will take only short runs, and I will stop it. As you see that flow rate is nearly constant, and the pressure drop is also nearly same. So now open the valve to drain out this water and close it again, and start from the beginning. So it will start from zero level, and so we'll take the second run 1 2 and start this stopwatch, and you will see that it is showing this will take for some time, and we will stop it to cut down the time. So it should take it up to 160 liter, so much more time to be used for this experiment. Now stop it here and close the valve and open this drain valve, because filling and draining time will take much more time. So we take a little time for this experiment, and we take third run 1 2 3 and start this stopwatch, and then thinking that it is almost constant, we stop this stopwatch and close the valve and drain this water out and close it, so that will start from the zero level again. And then we take the fourth run 1 2 3 4 and start this run, and then close it, close the valve and stop this watch and drain out this water which is accumulated here. So we close it, and again we'll take the fifth run 1 2 3 4 5 and start this stopwatch, and stop it and close the valve, drain this water out, and close this valve and take the sixth run 1 2 3 4 5 6 and start this watch. You see there is a change in pressure drop now appreciable, and stop this stopwatch, close this valve, inlet valve, and drain this water out. And close the valve. Now take the seventh run 1 2 3 4 5 6 7 and start the stopwatch. And now you close the stop this stopwatch and close the valve and drain out this water out. And close this valve. You take 8th run 1 2 3 4 5 6 7 8 and start, and wait for some time till this velocity is nearly constant or flooded. Now stop it here and close this valve and open this drain valve. And close it, and then again take the 9th run 1 2 3 4 5 6 7 8 9. You look this clockwise, it is opening, anti-clockwise it is closing, and now you can stop it, and then drain the valve. The tank has been drained. Now it is to be zero level, and then close it, and then again take the 10th run 1 2 3 4 5 6 7 8 9 10 and start. So we'll stop it here and close the valve and drain this water out. Now we close the valve, and again we will take the 11th run 1 2 3 4 5 6 7 8 9 10 11 and start. And then we take it for granted and stop here and close here and open this valve. And close it and take the last run, that is 1 2 3 4 5 6 7 8 9 10 11 12. So we got the last run here. So you can stop here and close this valve, and if you want to repeat all this experiment, you can drain it out again and you can start from zero level. And we'll not do this now, for whatever runs have been taken, mostly inaccurate because time was not much devoted to fill the entire tank or give much time for getting accurate results. So we'll do it, say it is kept ready for next set of runs if you think essential. Now click the clock. This is your calibration chart, which you can see this calibration for the rotameter for all these scales from 0.5 to 7 around. You will find the corresponding pressure drop in millimeter of mercury readings, and the corresponding flow rates are measured here. And you can see that these are most inaccurate because I have not given much time for the experiment. So here you will find the pressure drop in millimeter of mercury, 10 times magnified in its y-axis, and the velocity to the orifice in centimeter per second, which is perfectly parabolic in nature. It is because the time was not employed. So you will find almost the same flow rate here. Now here, this is for orifice plate. You will find this entity has been y-axis and x-axis is the velocity in orifice, and this is square root of 2g delta p rho 1 minus beta to the power 4 has been plotted in the y-axis, and the slope of this line has been measured, and the inverse of it is the coefficient of discharge of the orifice plate. So this I will find this 2g delta p by rho by 1 minus beta to the 4 according to Bernoulli's theorem. We can get this equation by energy balance, and we'll find that g for gravity, acceleration due to gravity, and delta p is pressure drop in millimeter of mercury, rho is the density of water, and beta is the ratio of the orifice plate hole diameter to the pipe ID inside diameter. That ratio is around 0.25 here, and we found that value of the coefficient discharge is 0.84. If you do this more accurately, giving more time for the experiment, you will get around 0.75. So that's all I wanted to show you how the flow meters can be calibrated. Thank you very much.